All right, so we have that. Anybody did not get? Oh, there's a little blue chart. Oh joy! You guys are gonna love this. And anybody still need the one with the pyramid on the one side? Let me find out. Hold on. You need which one? This here? You need this here? Oh, Same one. Yep. Which one? So just remind you guys, these Z-score charts are your Z-score chart. You need to bring them with you to tests and quizzes. Don't write anything on them, formulas, notes, or anything, because I will be looking at them, so don't do that. Just always have somebody put something on there. I didn't know. All right. Not sure what to do for that person. Ooh, add more lights. There you go. So we did the first half of this, and I think we did the first couple problems. Yeah. Good old problem number 4. Coming out of nowhere. No problem 2, no problem 3. Those are overused. Yeah, what do you expect? How's your weekend? I'm a little more awake than I was this morning. Oktoberfest out in Oklahoma. A few nights actually last night. A little too much.
Did you make a tower of cups?
No, but we contributed.
Yes.
Yeah. Why not? I love how they booed the poor dude walking around, taking him down, throwing him out.
Right.
It's like, he lives off your booze.
Right.
All right. Can you live off his booze? Circle of booze? No. All right. So, if you were not here and you have no idea how to read this Z-score chart, let me do a problem real quick for you to start off with. Oh, let's do... Let me get myself some paper here. Alright, so screw this. I'm just going to do an example. Saying what the probability that Z is greater than negative 1.91. So what does this chart tell you when you look up a Z-score? If I look up the Z-score, negative 1.9, so here's how you work it. Negative 1.91. This is the correct thing. Negative 1.91. So first off, do you guys see how that works? This is the first 2 parts, the first decimal place. And this fills in the second decimal place. Negative 1.91. 0.0281, but where is that on the picture? In fact, where is negative 1.91 at? What's right in the middle? Yeah, for Z-scores, it's 0 in the middle. So please, dear God, it's just a regular numbered line. You all should know number line. So when you put negative 1.91, it's right there. So when you get 0.0281, where is that area? What's the chart always tell you? The area that is below. And we want the area that is above. Greater than. It's a little arrow pointing in the direction you shade. If you want to think about it like that. So here is the 0.0281 right there. So how do I get the answer to my question? How do I get the rest of it? 1 minus that. 11. Sweet. So 1 minus 0.0281 is 0.9719. Now some of you guys might have gotten that answer quicker. That's awesome. You just use the little shortcut. You shave off like 6 seconds. I love it. So there'd be a 98% chance, almost, just barely over 97% chance that there would be a z-score over negative 1.91. Which makes sense because the mean cuts it in half. And you're going to get a lot more area to add on to that between those two. Okay, how are we doing there, you guys? I love you guys. Give them nothing to work with. Doing a good job. Okay. And again, I desperately tried to make this connection with you that it's all about the area. When you graph it, you have a visual representation of your probabilities. It's the area. All the chart does is gives us all the areas below a z-score. How did somebody calculate it? They used calculus. Because that's part of what calculus does, is some irregular shape. You can figure out the area below that. That's exactly what we need. So we're not going to do the calculus. We're just going to live off the calculator, the computer that did it for us, made this little chart. So for this problem, what goes right in the middle of any problem they're asking about?
7.81. No,
31.64, yeah, that's the mean. Underneath it, I'll put 0, because that's the z-score associated with it. So the difference between this problem and the problems that are up here is up here, I already knew the z-score, so I could just use the z-score chart immediately. Down here, I don't know the z-scores yet, so I got to make them first. So we've known the z-score formula for a while. So as long as the sucker is normal, I can make a z-score and look it up on the chart. I can always make z-scores if I know the mean and the standard, always. But what's the only time I can use this chart is if it's normally distributed. Because then I know a lot of shit about it. I know the shape of it. I know that's why this is so specific. Now I want to know between 15.5 and 19.5. So let's put them down there relatively in the right place. So I need to make how many z-scores? 2. So the z-score for 15.5 would be 15.5 minus 31.64 divided by standard deviation, 7.81. So it's x minus the mean divided by the standard deviation. Cool. And whatever the hell you get out of there. Negative 2.07. Crowdsourced, I like it. And then I got to make 19.5. Negative what?
1.5.
1.5?
5.
5? Thank you. It should make sense. They're both negative. Both numbers are less than the mean, so they're below the mean, so they're negative z-scores. I like it. So now if you look at the areas for these two, so what's the area below 19.5? You'd have to look up negative 1.55. So negative 1.55. 0606.
Yep.
0606. And then the area below this one, you'd have to look up negative 2.07. 0192. I like it. Please let this make physical sense. 0606 is too much area. If I cut off the 0.0192, I'll be left with exactly the amount of area that the question asked for. And the area, since it's a probability distribution drawn out, the area is the probability of something in there happening. So if you subtract those, what do you get? 10414.
Yep.
Sweet. So about a 4% chance that it took somebody that long over the course of a week to find a parking spot. Right, so that would, if it took somebody that long, they were one of the lucky ones. Okay. So let me show you this. I always show this in the hopes that it actually helps, because we're going to do something backwards here in a minute. Normally, I give you an X score. Right? These are X scores. 27.2 is an x. It's a data point. 53 is an x. These are x's. And what's the first thing I do with them? I turn them into z-scores. Because then if they're z-scores, I can look them up and get the probability. I like it. So this is by a formula, and this is by the chart. And of course, the only time that that little progression works is if it's normally distributed. All right. So notice part B of number 4 then. This is related to a problem we did earlier. Normally, a problem, I start out with a question about x's and I end up with a question related to the percentage, the probability of it happening. Here, I tell you the percentage to begin with. So we're trying to work backwards. What would put somebody in the 14th percentile? In this case, would that be a good place to be? Yes. On a test, 14th percentile would suck because only 14% made less than you. So you're like, well, some people did worse. Well, okay. But in this case, only 14% would have taken less time to find a parking spot. 86% took more time. That's a good place to be. Whatever you're doing something right. Coming early enough, or you're just being lucky all the time. Whatever. Or just parking in the faculty parking. Ticket the hell out of it. All right. Where is the 14th percentile in the picture?
Left.
Yes, the mean would be the 50th percentile, right? The median. So the 14th percentile's got to be way down here. Always put areas up top because they look like z-scores, those evil little shits, right? So you put those areas up top to keep yourself straight about, well, that's an area. So now watch what we're doing. I want you to realize what we're doing. We're going to do all this backwards. I love it. They gave us a percentage, so I'm going to look up in the chart to find the z-score, and then I'm going to use the formula to find the x-score. That's the great thing about math. It can go both ways. Don't judge. So 0.14.
Negative 1.08.
Yeah, what's the closest?
Negative 1.08.
Yeah, it looks like we get really damn close. I get 0.1401. That's what you guys got? Just get as close as you can. Can't get much closer than that. And that's going to be a negative 1.08, like you guys said. I love it. Is everybody able to see that? When they give you an area, and we need a z-score, you got to find it in the body. And you just get as close as you can. If it's right in the middle of 2, you can make it the middle one, just like they did with these little asterisk dudes, right? It happens a few times. It happens more times than this, by the way. So negative 1.08 is the z-score. I'm trying to find the actual time. I'm trying to find the raw score, the x-score. So what have we done so far? We looked up a percentage. We found the corresponding z-score. Now I've got to find the x-score. And before we do that, we're going to do a little bit of algebra. Because what algebra is really, really good at is solving when you don't have any values yet. And why the hell would you want to do that? Well, we have a formula for z-score. It's already solved for z. So if I know x, mu, and sigma, I plug them in. I got no algebra to do. I just put all that shit in my calculator. I'm done. So what algebra does is it says, oh, what if you don't know the frickin' x, but you know z? Wouldn't it be better to have a formula that x equals, so you don't have to do algebra every damn time you use it? Just do it once? Yes, algebra. You would like that shit. So how do I solve that formula for x? What would be a really good first step? I love it. You're just going to go through all the algebra. Yeah, what's the worst part about that equation?
Dividing.
Stupid fraction. And remember, the great thing about equations is you can kill fractions and equations because you're allowed to do stuff to both sides. So how do you kill the division by standard deviation by sigma? Multiply by sigma. Oh, algebra has a use? Who the hell knew that shit? Well, most people that know algebra know that shit. Wow. So then you get z sigma equals x minus the mean, and then you just have to do what?
Add the mean.
Add the mean. So now, this little formula will be one sitting on your formula sheets. And I really want to just take a second and try to point out to you, you're not allowed to have notes on your formula sheets, as some of you have found out, even though I just told you directly before, you found out by losing points. But this is a note. This is a note written in a different language. It's written in Mathish. So what does a z-score tell you? It's the number of these away from the mean to the data freaking point. Shit. No, yes. Start at the mean, and you go this many of these to get to the data point. Okay. It's an equation form of the definition of z-score, if you let it be. I don't know what else we do. Trying to tell you, I don't let formulas, I don't let notes on there, but I gotta let you write formulas down, and that's a note too. Holy shit! To help you answer the question that will be on every test that a lot of people got wrong, even though I told you it was going to be in class 6.
So you say you can or can't have that on?
Yeah, that's a formula. You can have that. Yes. It just happens. Huh?
Because you said no notes.
Exactly. No notes, but I gotta let you have formulas in the formula sheet, or else I'd be a real asshole. So that's got to be there. If you can just read it in English, it's a note. Okay. So how do I use it for right now? Well, what do we know? Do we know the mean?
Yes.
Yes. The mean was 31.64. Do we know the z-score?
Yes.
Yes. Negative 1.08. And do we know the standard deviation? Yes. 7.81. Yeah. Yeah, so 31.64 minus 1.08 times that. What is it? 23.21. 23.21? Whose? What's? Minutes, yes. Please don't. Some of you guys realize I already am a dork, but don't make me be more dorky. Don't not put units and just maybe put bananas, light years, shoelaces. I just put whatever the hell comes to mind. Please include the units. All right. So I want to do a few more examples of this, okay? Because this was just getting used to the chart, really, and this is just one example of a normally distributed thing. I want to do a couple more examples up on the board. We'll do a little preview of what's coming, and then we'll see what time it is. Head out, maybe. Oh yeah, maybe so. This is 6, yes. I think. Yeah, this is chapter 6. If that's the question happening. Thing available for that. So the heights of men in America, now of course in different countries it would be different. Heights of men in America normally distributed with mean equal to 69.1 inches and standard deviation 2.51 inches. So that's a population, this is population information. So let's see. Find the probably, if we pick one person at random, one In fact, this is hopefully you understand this is. I said, man, okay, then, man, if we pick one dude at random from America, right, what's the probability that that dude will have a height of less than 65 inches? So let's see. How do I draw this picture? I just want somebody to say poorly. Jeff, no. So what goes right in the middle of this little dude? How do I know I can do this? Draw this picture. How do I know I can even do this problem? Yeah, it says normally. So later this semester we're going to have to say, what if it doesn't say that? There's just something else that would cause something to end up being normally distributed. There's something I can check to see if it's normally distributed. And that's obviously a huge part, because like I said before, if I know it's normal, I got all the freaking answers just waiting for me. I just got to figure out where to look. I calculate the z-scores, know where to look. What goes right in the middle?
69.1.
69.1. Where's 65 at? Over here. And I want to shade where? Below it. Yeah, this little arrow. You can make sound effects if you want to. So what's the first thing I need to do after that, after I draw that picture? Yeah, got to make a z-score so then I'm able to use the chart. My chart only understands when I look up z-scores. If you're trying to look this up, it's going to freak the hell out. Yeah, so it'd be our data point. It's always minus the mean. You don't flip these suckers around because then you'll be on the wrong side. You get a different number you're supposed to. Divided by
2.51.
0.51. Is it negative 1 point? What is it?
63.
Negative 1.63? Crowdsourced it. So remember, if it's negative 1.635 or something, you have to round to 6.4. So you got to round that sucker.
633. It was 633.
633? I love it. So 1.63, I love it. I can't get that precise in my head. I'm just, in general, be sure you round those z-scores to 2 places. Why 2 places? Because the chart only knows out to 2 places. If I look that z-score up, I'm going to get an area. Will I be done at that point? What area do I want? The area that is below this? And the chart's going to tell me the area that is below that. Yeah, so I'll be done. So this is a z-score of 0. This is a z-score of negative 1.63. What do you get when you look up negative 1.63 on the chart?
0.0516.
Who did what?
0.0516.
0.0516. Yeah. So if you circle that, I'm happy. If you make it 5.16%, circle it, I'm happy. No, your goal is not to make me happy. Normally that equates to you understand it, you did it right. All right, so let me give you one to try on your own with this. Find the probability that the dude we pick is between 70 and 75 inches tall. Alright, let me catch up to you guys. So the first step is to give yourself an anchor, give yourself a picture. So I know the answer is going to be less than 50%. It's less than half of the picture. That's one thing it does for us, is it gives us an idea of what should be the answer around. The very first step after this now is to make z-scores so I'm able to actually find those areas. So the z-score for 70 0.9 0.36 0.36 and of course, why do we do 2 decimal places? Chart only goes to 2 places, so always 2 places. So I got 0.36 for that, and then the z-score for 75.
2.35.
2.35. What you said? Okay. So this will be 0.36, and this will be 2.35. So if I look up 2.35, that's way too much. But what do you get when you look up 2.35? What area?
9906.
Yeah.
99.6.
9906? Okay. And of course, to adjust that, I just got to subtract off the area I don't want in there, which is this one. When you look up 0.36, what do you get?
6406.
6406? Well, I like that. That's nice. Exactly. That's nice.
35%.
So when you subtract those, 9906 minus 6406, I like that. You get 0.35 or 35%. Wow. So there's a 35% chance some dude will be between 70 and 75. I want you to realize, here's a really silly example of why this is good, but hopefully you guys start to see how powerful this kind of thing is. The closer something is to normal, the more I can trust what I get from the z-score chart. So there's actually a little wiggle room where you can be not perfectly normal, but still get an idea. So if I want to know, how many candidates to become a jockey are there in a certain area, or how many candidates are there for astronauts, anything that has kind of like a height, and it's not really a height restriction on jockeys, it's more like a weight restriction, but still. If you have anything with a height restriction, or you're looking for somebody tall to round out your team or something, like how many candidates are there in the first place, what percentage? You can use this kind of analysis to do that. If you have the local area's mean and standard deviation, you can then get a feel for what percentage could actually fit into your requirements. So you go beyond height requirements. Any requirements, you can kind of do this kind of check to see if you're being too restrictive. If it turns out that only 0.2% of the population meets your requirements and you're trying to get more people in, like, what can we ease up on here, everybody? It's a little bit too restrictive. I don't know, you guys see what I'm saying? And I think I've already talked about like the increasing hip breadth, our ever increasing butts, and how you can figure out airplane seat width so that you get less complaints, or if your airline is even worried about that. You can do a study and figure out where to put it so that you can control the percentage of people that would complain that the seat is too small. You can figure out what percent you're okay with complaining, figure out what this is, and then that's where you would set your seat width to. Do you guys start to see how powerful this kind of thing is? Now again, stats 1 is based on it's normal already, or there's something that we can test to see if it's normal enough, or if it's close enough to normal. Stats 2 would be, well, if it's not normal enough or whatever, what else can you do, right? If we did a stats 2, we know. Okay, let's do one more problem with this, and then I think let's do one more with this setup here. Take this one away. Find the height that represents P 13. So this problem will give you a percentage. So the first thing you got to figure out is what z-score does that relate to? Because then I have a formula for how to figure out the data point related to that z-score. So it's that x to z to percentage thing just backwards. So where would P13 be? Yeah, down here. It's only got to have 13% below it. So down here somewhere. Wow. This is 0.13. What z? What's z-score?
Negative 1.12.
Ooh, dissension. So one of them is 14 away and one of them is 8 away. It's probably the one that's 8 away. 1292, so it's negative 1.13. I like it. Now, if you wanted to split the difference, that's great. It's not exactly in the middle, but I'll still accept that. If you want to do like I had to do and interpolate exactly what it is between the two and make a linear equation, it's not linear, so screw it. I would not do that. So this will be negative 1.13. Does everybody see that? So it's 1314 or 1292. Which one of those is closest to 0.1300? 1292 is closer. Right, that's it. That's all. Just get as close as you can. It's like a Price is Right game. So that's the z-score. How do I figure out the raw score that relates to? I just got to throw it in there. Somebody, you guys okay? You guys understand? You guys, what's up? Which word? So everybody cool with P13 being here and that being 13%? Is everybody cool with that step? Because that's what percentile means, the percentage below that thing. So P13 is the z-score that has 13% below it. That's what it means. So I can draw the picture immediately based on that. So if I said P77, you would put it up here and there'd be 0.77 below it. That's what percentile means. So if that's the part you don't understand, you got to come see me because that's old news. Okay. When I look up 0.13 in the chart, it's not a z-score, is it? It's an area. So you don't look up 0.13. You look up in here. That's where the areas are. That's where the percentages are. So the closest I get to 0.13 is 0.1292. It's the closest to 0.13, and that would be what z-score, where you look out to see what z-score it is. This is z-score negative 1.13. You look at 1292, you look out, negative 1.13. That's what the z-score is. Boom. And now you put everything into your formula. The mean is 69.1 minus 1.13 times 2.51.
66.26.
What is it?
66.26.
66.26? Inches. So 13% of American men have a height of this or less. Okay. That's enough of those kind of problems. I want to do a little preview of what's the next thing. And the next thing deals with what I was talking about if it's not exactly normal, what might make it normal. So we got this here. So I'm going to do something I didn't get to do earlier this semester, but I'm going to do it now because it works beautifully for this. And that is, and if I went to Parallel World Florida and I asked people how old they were, one possible distribution I might get, and this is a parallel world, just so it explains what's going on. So I could get people that were just born, right? Maybe they have somebody answer for them. So a big group of people that are younger, somebody younger, 0 to whatever, and then a big group of people that are older, because a lot of people go to Florida to retire. Right? How are we doing? Where's the mean at, roughly? Yeah, somewhere in the middle here. And maybe it's a little closer to that because it's a little taller. You guys, so far, so good? So let me give us, if you feel better, I'm going to put some stuff up here. There's a 110-year-old dude there. Let's say the mean is like 40. Let's say 40, sure. Why not that? Okay, no attention to my scale, just leave me alone. Okay, those numbers up after. All right. So how did I create this picture? How would this picture, now, if I actually did this, went to Parallel World Florida, like Universe B128, and I go to Florida, that universe, and I start talking to people, how do I create this picture? I ask somebody, how old are you? And they say, I'm 87. What would I do with that information to start making this picture? That's the first person I talk to. What would I do? I'd see 87. 87 is like right here. And I put a dot. 87. You got somebody else. How old are you? I'm 2. Okay. And a quarter. Okay. So I put a dot. You guys with me? So the dots are individual people that I'm talking to. And so why was this so high? Because there are so many people that are that age in Florida. And why was this one so high? I just want to do that. All right. And what's happening in between these two? Ain't no one aged that. Right? Just happens to be in this parallel universe. It's some kind of weird take on Logan's Run. No? Okay. All right. Is everybody with me about this so far? The setup. All right. Okay. So this is taking one person at a time. What's going to happen if I take, let's say, 20 people at a time? not just one, but what I do is instead of doing a dot for a single person's age, I do a dot on the average of the group of 20 that I've picked. So I pick every possible group of 20 people from this parallel world, Florida. I say, calculate your average age amongst yourself. Right? And I've got the full authority of the government. They got to do it or else they get put to death. Right? This parallel world, I love it. What would be the most likely thing to happen if I randomly pick a group of 20 people? Am I going to get a bunch of 2 and 1 year olds? Just randomly happen. Is that going to... Not is it impossible, but is it likely for that to happen? What is the is that likely to happen? If I randomly pick people, I'm going to get a bunch of 1 and 2 year olds just from randomly picking. That would freak me out a little bit. Right? So not very likely. What is the most likely thing? Yes, yes. Yes, I love it. So the most likely thing is I'll get, a little bit of both. So what is the most likely outcome of the average of a group of 20 people? It's the freaking average, right? So in this new picture I'm about to draw, where should be the tallest peak? The freaking average, because we just said it's the most likely thing to happen, right? In fact, that's really why the average is called the expected value for any group. Is the average the most likely thing to happen for an individual? No, nobody's 40 here, right? You get killed here. But if you move in after this age, you're okay. I don't know. Like I said, look up Logan's Run. All right? Weird take on it. So when I draw this, I'm going to say, how old are these 20 people here? And they'll say, we're whatever. Right? But the most likely answer to that question is going to be here. So that's what we're going to. So maybe the second most likely thing to happen, you guys see, would be around that peak there. You guys see that? So when I draw this, maybe it's going to be like a little bump there, and then a big bump there, a little bump there for that. Okay, you with me? Now I know this is me drawing this and making up a parallel world or whatever, but it doesn't. If there was a distribution that looked like this, the same kind of thing would happen for it. When you start taking samples, what the interesting thing that happens is the resulting graph of the averages becomes more normal. Right? In fact, this guy has some standard deviation, right? He's got some standard deviation. How does this standard deviation compare to that one? There ain't a soul up here that is the average. Here, most of the groups are the average. So what's going to be true about this guy's standard deviation versus this guy's? Is it going to be more or less or equal? Because what's the standard deviation tell you?
How far apart it is from
The average distance from the mean. Ain't nobody here that is the mean age. Most of the groups here have the mean age. So the standard deviation here is going to be smaller. Of course, it gets smaller. Everybody kind of rushes to the middle. I love their reaction. If that doesn't make sense yet, okay, let it sink in your brain. Right? But if there are a lot more people here, then the distribution is less spread out. Which means the standard deviation, this new standard deviation, will be smaller than the old one. I'm going to call this sigma sub x bar. What the shit does that mean? That's the standard deviation for all the means I got from my samples. And what's the symbol for the sample mean? X bar. So I don't know if you notice this, but whenever you do 1-var stats, it doesn't just say sigma, it says sigma x. So that means standard deviation of individuals. Right? So sigma x bar means standard deviation of groups, of samples. So how did I make this picture? If I would have done this really and traveled to this parallel Earth, I would have taken a group of 20, got their average, plotted. A group of 20, got their average, plotted it. So this is how the averages are spread out. Now here's the neat thing. No matter what the hell the original looks like, once you hit more than 30, so if I said n equal 35, your result becomes normal enough. Kind of smooths out the bumps. It's really neat, no matter what it started off looking like. Once you get around 31 and what more than 30, then the whole thing becomes normal enough. Well, that kicks ass. So if we get a sample size of more than 30, and I'm asking questions about the averages, I'm allowed to use that chart. That's the whole thing. That's beautiful. Oh my God. So. The thing that we have to investigate now is how exactly, I know that is less than this. And I know even for this, it's going to be still even more less than. It's going to get even smaller. So it seems that the bigger n gets, the smaller my new standard deviation gets. So the formula ends up being this. It equals the original one, divided by the square root of n. So as n gets bigger, that's going to get smaller. So it shrinks by a factor of 1 over square root of n. So let's do one, well, maybe. Let's do this. I want you to realize something. That took me a while to talk about, right? I had to go to freaking parallel universe and shit. Right? At least in our imagination. Oh, imagination. But the really funny thing about this idea is, if they take a sample, so if they say, we take a sample of 40 Americans, what's the probability that their average height is more than 70 inches? So they took a sample, and they're talking about the averages, right? What do? I do all the same work I did before, but I don't use the standard deviation they gave me. I use the new standard deviation, the one that works for groups. This is the one that works for individuals. Well, what's the one that works for groups? It's this one. So if I have a group of size 40, I got to use sigma divided by square root of 40. That's going to be my new standard deviation. That's going to be what goes underneath for the z-score. All the work's the same. Holy shit. Every step's the same after you change the standard deviation, and then you make a z-score, you look it up in the chart, you adjust it if you need to. All the steps are the same. There's only one change. Change the standard deviation. Because it is going to get skinnier. Craziness. All right, so that's what we'll do some of next time. And obviously I'll have your quizzes graded on Wednesday. Anybody still need to, please don't leave me your ID. Yeah. So P13, so I mean 13% in here. So what's the closest? This is where the percentages are. This is closest thing to the 0.13 is right here. That's the closest thing to the 0.13. And that's negative 1.13. That's the z-score. Negative 1.13. Yep. Oh, this one? No, which one? This, you got this here, right?
I don't know.
You don't have this? And this one you don't have? Okay.
Alright.
So Travis? Yes. Yes. Cool. Yeah, the new one is the original one divided by the square root of your sample size. Gotcha. Okay.
Thank you.
So it does go decrease as your sample.
Question regarding the quiz. So when you ask us for the minimum and the maximum, why do we have to go 2, not 1?
Because one would, in a normal distribution, with going out 1 would leave 32% out. So I wouldn't say that's unusual. If something has a 32% chance of happening, so yeah, if you go out 2 steps, then you only leave 5% out there. Then something happening out here, yeah, I'd say that would be unusual. Okay.
Thank you.
Sure.